This video is about the derivative of x squared. The derivative of x squared is 2x. We could derive this algebraically quite easily, but in this video we'll gain some intuition for why this is using geometry. I will assume that you have a basic understanding of what the derivative is, and that you will recognize the definition, but nothing beyond that. There are 5 parts to this video. The first is an informal explanation of the derivative of x squared. The second is an informal explanation for x cubed. Then we'll prepare for using the definition. Then I'll show how using the definition leads to the same result. And then last, I'll talk about the general case briefly. To begin with, we'll start with a square with side x. It has area x squared. So instead of thinking of x squared algebraically as symbols, we'll think about it geometrically. We'll say that x squared is a geometric square with side x. This is why x to the power of 2 is called x squared. What is the derivative of x squared then? It's the rate of change of the area of the square when x changes. It's not a specific difference between the two different squares. Here, the orange part is the difference between this square and the larger square. The derivative is more like the change in area when you make the smallest imaginable change to x. So we'll make this orange difference as small as we can visualize here on the screen. When you do that, the difference looks like 2 line segments. This line segment has length x. This line segment also has length x. Therefore, the total change is these line segments combined, 2x. The 2 is because there are 2 line segments. That's because the square is 2-dimensional. It grows in 2 directions, the left-right direction and the up-down direction. The x is because the square grows by adding small line segments, each with length x. And that's the geometric explanation for why the derivative of x squared is 2x. Now, can we make the same argument for x cubed? In the same way, we'll think of x to the power of 3 as a cube, with height, width, and depth all being x. That's why x to the power of 3 is called x cubed. A cube grows by adding the thinnest imaginable squares to the sides of the cube. Since the cube has side x, each square has area x squared. There are 3 squares, because a cube grows in 3 directions. Each square has area x squared, so in total, the cube grows by 3x squared. Therefore, the derivative of x cubed is 3x squared. I'll show how this just follows from the definition of the derivative, but first some preparation. The first thing is that x times h is a rectangle with sides x and h. It has area x times h. So think of a multiplication as taking 2 line segments and making an area from them. The square is just a special case of this. The second thing is that when you have a rectangle x times h, you can divide it by h. Then the result is back to a line segment with length x. That's just saying that x times h divided by h is x. The expression x plus h squared can be described geometrically too. It's a square with side x plus h, but we can divide it into parts. The total side is x plus h. This part is a square with side x. This part here is a rectangle with area x times h. This part here is also a rectangle with area x times h. This final part is a square with area h squared. The total area can then be written in 2 ways, x plus h squared, or the different parts added together. This is why x plus h squared expands to this expression that I'm sure you've seen before. So the definition of the derivative is this expression. We'll use this and think about each part geometrically. In our case, f of x is x squared, so we'll replace f of x in this expression. First, x plus h squared is this square, as we already established, with these four parts. This other term is just x squared. Subtracting them leads to this. What we're left with are three parts. Two rectangles with area x times h, and one square with side h. The next step is to divide by h. Dividing by h turns these into line segments. Two line segments with length x and one with length h. The final step is to take the limit as h goes to 0. The two line segments x don't depend on h at all, they remain unchanged. But this line segment h goes to 0 as h goes to 0. It disappears. What we're left with are two line segments with length x. The final result is therefore that the derivative of x squared is 2x. I'll reiterate what this means geometrically. The 2 is because there are two line segments. That's because the square is two-dimensional. It grows in two directions, the left-right direction and the up-down direction. The x is because the square grows by adding small line segments, each with length x. So what about the formula for a general polynomial x to the power of n? We'll extend the same argument to this. Think of x to the power of n as an n-dimensional cube. I can't really draw that here, so you'll have to imagine it. This cube grows in n directions. It grows by adding thin slices of n-1 dimensional squares. Each of these slices have an area x to the power of n-1. Therefore, the formula for the general case is n times x to the power of n-1. I hope that this has given you better intuition for why the derivative of x to the power of n is the way it is.